So far what we have seen, now I'm going back in history and back in the past and starting as if I just finished module 23.2. So far what we have seen is that an intuitive explanation of Gans, you had this generator, a discriminator, you had this minimax objective function, which you minimize with respect to the parameters of the generator and maximize with respect to the parameters of the discriminator. And then we saw this overall algorithm for training them, which alternates between the generator parameters and the discriminator parameters, okay? Now, we want to look at some math behind this intuition, right? So all we have done is we have set up an objective function and just assumed all of that will work. We have not even defined what does it mean by saying at the end the GAN that we trained actually works. What does it mean? So let's start with that, right? So we'll delve a bit deeper into this objective function and see what it implies. So suppose you have this true data distribution, right? So you are given this training samples, right? And from these training samples, these are all the MNIST images. Each block is one MNIST image. You have these training samples, and these samples actually come from some distribution, right? On the other hand, you have this generator, which is also generating images. And I can say all of these images are coming from another distribution, which is P of Gx. Both these distributions are on top of X, where X is your images, 1, 0 to 4 dimensional or n dimensional. So both these distributions are over the same set of random variables, but one is the true distribution, one is the generated distribution, okay? If everything works fine, what do you want to happen at the end? Pgx is equal to P data x, right? That's what we mean when we say that it should work, okay? But is this the objective? If that was the case, we should have said this as the objective function, right? We should have said that minimize the KL divergence between these two or whatever other probability distance function that you know of, right? But we didn't do that. We used some other cryptic objective function which depended on some cross entropy or some score and so on, right? So what we need to show is that, and the reason we did that is because we did not have a PGX, right? We did not explicitly model PG of X. Unlike autoregressive models or RBMs or VAs, there was no P of X in this generator, right? We never came up with the formula for P of X. So that's why we couldn't have that as the objective function. All we can hope for is that whatever this pseudo objective function we have set up, that eventually leads to this condition, even though we have explicitly not computed P of X or P of Gx. Does that make sense? Is it okay what we need to actually show? Is that clear? Okay, right. So what you want to say is that, so here's, let me state it this way. You want to show that if the discriminator's loss function is at its minimum value, can I guarantee that that can happen only if Pg is equal to P data? Is that fine? Is that a good statement? Okay, so we'll try to prove that. Okay, so here's this theorem statement, right? This is from the paper, that the global minimum of this training objective, right? And this max V of GD is nothing but that two-part objective function which I had written, right? So this V of GD is just that two-part objective function which I had written, where you have an expectation over the true samples and an expectation over the generated samples, right? And I'm trying to maximize this with respect to the discriminator, and I have to show that. So actually, so here's the theorem, and I'll just explain what it means. So remember that the goal of the generator is to minimize the maximum of this value, right? It's first you have the discriminator, you compute some loss function with respect to that, and the goal of the generator is to minimize the maximum value of that. Is that fine? Because it's minimize of maximize. Is that fine? Everyone is okay? So now the theorem states that this minimum will be achieved if and only if Pg is equal to P data, right? So what it means is that whatever objective function I have set up, if I'm able to achieve that objective function, then I can be sure that Pg is equal to P data, which should have actually been my true objective function. Is that fine? Is the statement of the proof clear? If I prove this, then you'll be fine that, I mean, we have gone back to our original goal and proved it, okay? Now, any theorem which has an if and only if part can always be split into these two parts, right? The if part and the only if part. So the if part is that if Pg is equal to P data, then the global minimum of the virtual criteria would be achieved, right? And the only if part is that if this is achieved, then Pg has to be equal to P data. There is no other way that could have been achieved. You get the difference between the if and only if part? So if Pg is equal to P data, then this will go to its minimum. That's fine. But the if only if part is the reverse of this. which means that if I know that this has gone to the minimum value, then I can be sure that PG has to be equal to P data, right? So I have to prove the if part as well as the only if part, okay? So here's the outline of the proof. We'll first look at the if part and then we'll look at the only if part, okay? So the if part, to show the if part, I have to show the following. First I have to find this value of DG when PG is equal to P data, because that's what the if condition says, okay? So I'll find what this value of VDG is, or rather actually CG is, okay? Then I'll find the same value when PG is not equal to P data, okay? So I know what the value is when PG is equal to data. I know what the value is when PG not equal to P data for any PG, any other PG. Now what do I have to prove the if part? First one is always less than equal to, right? Minimum. Is that fine? So when PG equal to P data, whatever value you get, that's always less than equal to the value when you get when PG is not equal to P data. Is that fine? So that's the third step that I need to prove, that show that A is less than equal to, less than B, or less than equal to is also fine. Is that okay? Everyone gets this three parts? I'll show what the value is when PG equal to P data. I'll show what the value is when PG not equal to P data. And then I'll show that A is less than equal to B. If I can show that, then I can show that the minima is attained only when PG is equal to P data. Is the outline of the proof clear? Does that make sense? Anyone who does not get that? Please raise your hands if you get this. Okay. Now the only if part is that when this minimum is achieved, I need to show that PG is equal to P data. That means if someone tells me that I have achieved the minimum, then it has to be the case that PG is equal to P data. Is that fine? The if part and the only if part? Okay. So let's start with the if part and we look at the first step of the if part. So this is the objective function. Now what I'm going to do is I'm going to replace the expectations by their integrals. Okay? And now I'm going to observe that, first of all, observe that this is nothing but x. This is the generated x. Right? So I know that this g phi of z is a function of z. So by this some cryptic rule actually, I can replace the second integral, which was over z's, by an integral over corresponding x's. Is everyone okay with this? The first integral has been copied as it is, but the second integral has been replaced by a different integral. Instead of z, now I have an integral over x. Why does this make sense? What is the rule that I've used here? I've used change of variables. That's a valid answer, but there's a slight problem there. When you do change of variables, you have to assume that the function is invertible. We don't know whether g is invertible or not. Right? Okay? So I'll give you an intuitive explanation for why this makes sense. This actually comes from something known as the law of the unconscious statistician. I don't know who named it that way. But I'll give you an intuitive explanation for why this is okay. Right? So we'll try to understand what this integral tries to do and then say that it's okay if I replace it by this integral. Okay? So the first integral is actually over z's. So these are all the z's that you have. Okay? Now given a z, is g phi of z a deterministic function or a random function? A deterministic function. I'm going to pass it through the neural network. For a given z, I'm always going to get the same x no matter how many times I pass it. Okay? So from the z domain to the x domain, what kind of a function do I have? Many to many, one to many, one to one, or many to one? Can two different z's give me the same x? Can two different z's give me the same x? That's possible. Think of a simple neural network which just does classification, right? You could give it two apple images. For both of them, it can give you the same output, right? So for two different inputs, I can get the same output. But for the same input, can I get two different outputs? No. So then what kind of a function is this? Many to one, okay? So there could be many z's here which correspond to the same x here, okay? Is that fine? Now, this integral is actually over the z's. I am integrating over these z's based on their individual probabilities. Is that fine? But now if I look at the x's, their probabilities are actually just a function of these two, because these, if I just sum up these two z probabilities, I'll get the probability of the given corresponding x. Does that make sense? If all of these are say 0.1, 0.1, okay, and only these two z's result in this x, then what's the probability of that x going to be? 0.2. Does that make sense? Okay. So now instead of summing over these z's, I can just sum over the x's and replace the probability of z by the probability of x, right? Because when I was summing over the z's, I was summing over these 5 terms, but it turns out that these 5 terms just collapse to 3 terms in the x domain. So instead of summing over these 5 terms, I can sum over those 3 terms and replace them by the corresponding probabilities. Does that make sense? Please raise your hands if it does. So that's the intuitive explanation for why this works, and there's actually a law behind that. You can go and prove it more formally, but if you understand the intuition, that's fine. I don't care if you don't really know this law, because even I don't know it. Okay. So that's how you will replace the z's here by x's here. And the reason I'm doing that is I already have one integral with respect to x. So I wanted the second integral also to be with respect to x. And the second thing was I wanted p data and pg. So I now have p data and pg. Does that make sense? Okay. And remember, this pg is actually a function of pz. You can write it as that. Is it okay? Fine. So now this is our revised objective function. Okay. Now when will this achieve the inner thing, right? If I look at this, when will it achieve its maxima? When for every given x, the term inside the integral is maximized, right? So instead of integral, just think of it as a sum. So you have a sum of some terms. You want to find the maximum of this sum. So the sum would be maximized when every term in the sum is maximized. Does that make sense? Okay. So then I just look at the quantity inside the integral, and I'll take its derivative with respect to d and set it to 0. Okay. So I'll take the derivative with respect to d and set it to 0. Okay. Can you help me in working this derivative? What will be the first step? P data upon 1 by p data upon dx into 1 plus pg over, okay, I'll just write it. Is that fine? Okay. Now I can just do some simple, I'll take one term on one side, okay, and I want an expression for d theta x. Completely sure, it looks like it matters, but I'm not completely sure of the implications of that, right? Whether it matters to this achieving its final objective or not, I'm not sure. That I need to work out, okay? So we'll come back to that. Let's not confuse the others about that, okay? So for now, just see that this thing, right? So you get the optimal discriminator. What is this d theta of x? Is it a distribution? Is it a score? What is it? It's a score. So what does it mean? That I will give you an x, the score, the best score that the discriminator should assign it is just take p data of x and divide it by pg of x plus p data of x, right? That's the optimal discriminator. Is that fine? Okay. Now, for any given generator, if I give you the generator, then the optimal discriminator is given by this. Okay. But what is the condition that we had in the if part of the theorem? P data is equal to pg. So if I substitute that here, what do I get? Half, right? So that's why when you end training, your discriminator should actually, irrespective of whether it's a true image or a fake image, it's so confused that it just assigns a score of 0.5 to both. I can't really distinguish, so I'll just say with half probability that this is real or half probability that this is fake. Okay, that makes intuitive sense. Okay, so now this quantity, right, that we were interested in, or rather the max of this quantity, I'll just substitute the max for each of these guys inside, right? That's the one which we have computed here. So I'll substitute that, and this is what I get. Okay, is that fine? What is this integral? What is this integral? 1, right? Integral over a probability density function. What is this integral? 1. So what's the final answer that you get? Oh wait. Oh, this should be plus, or I think, no, this should be minus, sorry, right? So what you'll get is minus 2 log 2, which is minus log 4. So this is the value you achieve when PG is equal to P data. So I have computed the value that you will achieve when PG is equal to P data. That was the first part or the first step of my proof. Is that fine? Now what do I need to do? When PG not equal to P data, what happens? Right? So that's why we'll go to the second part. We have done the first part. Now we'll look at the second part. So we'll throw away this assumption that PG is equal to P data. Okay? So we'll look at PG not equal to P data. So let's see what happens in that case. So I am not going to substitute half here because half is only when PG is equal to P data. So I'm going to work with when PG is not equal to P data. Okay? So now, since I know that somewhere I need to compare with a log 4, so this is some trickery that I'm going to do. I'm going to add this term, and you see that what I'm adding is just a 0, right? Because it's log 2 minus log 2. I'm just adding a 0. So this is a fair thing. I'm only doing this because I know where I need to reach. So I'm just trying some manipulation so that I reach where I want to reach. Okay? So this is not something which you can come up with. This is because you know what the answer is, so you have added this to. I'm sure all of you have done similar proofs in different high school courses and so on. Okay. Is that fine? I've added this. Effectively, I've just added a 0. Now what I'm going to do is I'm just going to rearrange some terms here and there. Okay. So first note that I can take this minus log 2 and this part as one integral. Okay. Is that okay? And then each of these other log 2's, I'm going to split it between the remaining two integrals. Don't try to really squint and try to understand this. This is very, very simple. I genuinely mean that. It's just some rearrangement of terms. And once you do all this, right, what you will end up with, okay, let's not go there. So you will end up with minus log 4 plus some quantity. Can you tell me what this quantity is? First, what is this? It's a distribution. What about this? Distribution. What does this term look like? KL divergence between P data and the term inside the bracket. And what about this? KL divergence between PG and the term inside the bracket. Everyone gets that? Right? So you can just think of this as P and this as Q. So you have integral P log P by Q and integral Q log Q by P or whatever, right? So you can just write it as some KL divergence, okay? So it's actually the KL divergence between P data and this other distribution. Is it okay? So you have minus log 4 plus 2 KL divergences, okay? So when PG is equal to P data, this value was minus log 4. When I don't assume PG is equal to P data, I get minus log 4 plus 2 KL divergences. So given these two statements, what can you tell me? What do you know about KL divergence? Always greater than equal to 0. Now can you tell me something? Okay, so let's look at the steps. So now at this point, what I've done is I've done the step 2 of the theorem of the proof. I've shown you what is the value when PG is not equal to P data. Is that fine? Okay. Now what I need to show you is that the minimum is attained only when PG is equal to P data. Okay. So the general term is this when for any PG, any P data. Okay. Now what do we know about the KL divergence? Greater than equal to 0. So what can you say about CG? It's always going to be greater than equal to minus log 4. That means minus log 4 is the lower bound. It's the minimum value that CG can take. And when did CG take that value? When PG is equal to P data. So what have we proved now? We have proved the if part. If PG is equal to P data, then CG takes its minimum value. Is that fine? Everyone gets that? Okay. So that's the end of the if part. Now for the L or the only if part, what do I need to show is that if CG has taken its minimum value, someone has told me here's the CG and it has achieved its minimum value, then it has to be the case that PG is equal to P data. Okay. Now what's the minimum value of CG? Minus log 4. We know that. Okay, so let's start with that. So the general formula is minus log 4 plus this. Now someone has told me that CG has attained its minimum value. That means what do I know? CG is equal to minus log 4. That implies the two other terms are 0. So KL divergence of this and KL divergence of this is equal to 0. Okay? So you can now prove that since KL divergence can only be greater than or equal to 0, so these two terms cannot cancel each other, so they both have to go to 0. And you can easily prove that this will happen only if PG is equal to P data. In fact, you don't even need to prove that. Whatever I have written here is actually the symmetric version of KL divergence, and it is known as the Jensen-Shannon divergence. Okay? So this is actually the Jensen-Shannon divergence between P data and PG. And the Jensen-Shannon divergence would be 0 only when P data is equal to PG. Okay? So whichever way you want to prove it, you can prove it. Either prove that this is equal to 0, I mean this equal to 0 implies that PG is equal to P data, or just assume that this is equal to Jensen-Shannon divergence. Not assume that, that's the actual relation. And that will be 0 only when PG is equal to P data. Okay? So have we proved the if and the only if part? So what have we effectively proved? That whatever objective function we have chosen, this minimax problem that we had chosen, actually optimizing that is the same as optimizing this other objective function, which is PG should be equal to P data. That's what we have proved. This guy will attain its optimum value only when PG is equal to P data. Is that fine? Right? So that's the more formal proof about why the particular objective function for Gans. Okay? So with that, I finally end the lecture and the course. So thank you, and I hope you guys enjoyed it, and I hope you guys learned a few things, and I hope you guys do well in the NSEM and on the remaining assignments also. So this NSEM will again be of the same flavor as quiz 1. It will not be of the same flavor as quiz 2. Okay, thank you.